Hello everyone and welcome to the Central NC Math Group Week 3 Problem of the Day lecture. This is going to be part 1 of 3 of a 3-part lecture. Useful counting principles is going to be the topic for this week, and so let's begin. So there'll be 3 topics covered in this video. Well, not this video, but in this 3-part series lecture. In this video specifically, we're going to be covering the balls and urns method. If you already know what the balls and urns method is, you're probably not going to get much benefit out of this video. We're going to be covering applications and restrictions with it, so if you don't know those, it might be a good idea to watch this video. But if you know how to do most of the problems relating to these, you probably do not need to watch this video. And now the recursion states video are the ones where I go into more complicated examples, so if you do want to come back for those, that'd be a good idea. So without further ado, let's get into it. So balls and urns counting technique used to count the number of ways to do certain things in certain cases. I'm not going to provide you with the formal definition. It's much easier to show through examples. And so let's actually do some examples here. And so we have a problem here. How many ways are there to place 10 indistinguishable balls into 5 distinguishable boxes? Well, right off the bat, there's a lot of orientations. You can place, 1 ball, 2 balls, 3 balls, 3 balls, 1 ball. It's like one orientation. They're distinguishable boxes, so you can even change that around. Basically, there's a ton of orientations to do this. So let's try to find a better way to do this problem. And so let's actually try to do something with spaces. So let's have some spaces for our boxes. So this is going to be box 1, 2, 3, 4, and 5. And we can place balls here. 1, 1, it's 4, and then you can have 7, and then 10. And this is in one orientation of putting this away. And there's a ton of them, and so we're wondering how we can actually do this problem to count all the possible values without going into some bash and some casework. So what I'm going to do is actually, interestingly, we can go ahead and consider the sequence over here. This particular sequence, it's right here. If we can find the number of arrangements of the sequence, then I think we get the number of ways to get the box. And there is a one-by-one bijection here that relates the dividers, having the space. Because you can have 0 balls in a box. There's actually, the arrangement of this should give you the answer. And that's where this balls and urns method comes from. Organizing dividers and objects in such a way that you can solve the types of problems that are explained here. So let's actually solve this. There's 10 total balls and there's 4 total dividers. So that gives us 14 total objects. And if you want to have number sequences, if you choose the locations of the 4 dividers, then that'll force the locations of the balls in the sequence. So it's just 14 choose 4, and that'll be your answer for this specific problem. And similarly, doing this, we can go on and we can write a formal definition for the balls and urns method. And so for undistinguishable balls and k distinguishable boxes, we have, as we said before in the products, k minus 1 dividers, so that'll give us k spaces. And we have n balls. We can solve this similarly as we did the last problem. We're going to have n plus k minus 1 total objects, and we can choose the number of the locations for the dividers, and that'll force the locations of the balls in the sequence. Or you can also do that for the balls too. It gives you the same result. Same thing, as this is a binomial property. So that's your formal definition right there for balls and urns method, if you really want to do that. But that's basically this for no restrictions, and you can see the no restrictions method is really easy. But obviously it's math, there's going to be some restrictions. Let's do a problem with restrictions. So how many ways can you place 10 indistinguishable balls in 5 distinguishable boxes if each box must have at least 1 ball? Now we're wondering, how can we account for this case? And one way to do that is actually, what if we just disregard the balls in each box? We have 5 boxes, right? And you have one ball in each box. Well, there's always going to be at least one ball in each box. So what if we just disregard those 5 balls? And then if we then we can have 0 balls in the box. We can have like a solution there. So we can disregard those 5 balls and this condition goes away. And so now we just have how many ways can you place 5 indistinguishable balls in 5 distinguishable boxes? And we know from our solving that we have 5 balls and 4 dividers, total 9 objects, and you can just look at the 4 dividers to give you 9 choose 4. It's a bit of bad writing there. And yeah, that'll give you 9 choose 4 as your answer for this. This is a lower bound restriction. This one could be anything, and you can just remove that many times these boxes is and get your answer. And that's why knowing how to actually do this without blatantly memorizing the formula is a good way to solve these type of problems with restrictions. Speaking of restrictions, let's get into a more interesting restriction, and that is how many ordered pairs of non-negative integers w, x, y, and z exist such that w plus x plus y plus z equals 10, and each of w, x, y, z are less than or equal to 4. And this condition right here is interesting because it's an upper bound, not a lower bound, so we can't disregard it or anything. So first, let's just write out the equation over here. First thing that comes into mind is complementary counting. We can count the number of solutions total for this equation right here, and then we can subtract the ones that have higher values. And that's going to start getting complicated quick. So let's say, is there a way to simplify this? And a good way to do this would be to set new variables such like 4 minus w. And why this works is if you have w equals 0, 1, 2, 3, or 4, you'll get a is equal to 4, 3, 2, 1, or 0. So a will have the same restriction as w, but you're simplifying the equation, and we'll see why later. Because if we go ahead and finish this process with the other variables, and we add these up, we're going to get a plus b plus c plus d equals 16 minus w plus x plus y plus z, which is equal to 16 minus 10, because we know the value of that equation is 10 right there. And thus this is equal to 6. And it has the same exact restrictions as w, x, y, and z, that a, b, c, d must be less than or equal to 4. And we have just greatly simplified this equation. And so now we can actually consider the extraneous solutions in an easier method now. So let's first find the number of ways we can number solutions to this Diophantine equation. And there's 6 balls and 3 dividers. So that's 9 choose 3, which I'll actually calculate out for you this time, 84. And now we can see to find the extraneous solutions, because if one of these variables, I'm just going to fix a as an example. If a is equal to 5, then w must be equal to negative 1. And if a is equal to 6, then w must be equal to negative 2. And we can't have negative solutions. So you have to remove those cases. So that's the case if one of them is 5, and then thus another one must be 0. Another one must be 1, and then the rest must be 0. Or you have one of the variables be 6 and the rest be 0. Number of ways for this is you can pick one of the 4 variables to have the value of 5, one of the 3 remaining to have the value of 1, and you get 12 for that. And then for this is just picking a variable that takes the value of 6. That's be 4. So there's 16 solutions that do not work for this equation, so we can subtract that out, and we get an answer of 68. And that's an example of an interesting restriction that's on this problem. And so let's move on to our final problem of the day. And I'm going to leave this as an exercise to the reader, and then I'll solve this at the end of the video. And this is a very nice problem, and does involve balls and urns. It doesn't, it seems like off the bat that it doesn't, but it actually does involve balls and urns. It's a very intuitive way way that it's incorporated here. Problem is 12 points are evenly spaced around a circle. How many non-congruent, non-degenerate triangles can be made such that the vertices of a triangle are all one of the points on the circle? So, I encourage you to try this problem on your own. Pause the video. I'll give you a hint later. So I assume you've tried the problem, and so let's actually take a look at this, and I'll give you a step that can get you started in your problem-solving process, and that would be a hint. And let's consider a circle here, and say we drew a triangle. I'm not going to draw the points because that'll be a bit complicated, but you see this, right? Well, if you actually go ahead and draw this out on your paper with the points, you'll notice that there's a certain number of points between vertices, and you can get that for all three of these. And the number of points between vertices, like the spaces, because there's 12 spaces. Am I right? There's 12 spaces between vertices. Uh, if there are 12 spaces like that are total around the circle, you can have spaces around vertices, and so if you actually add up the spaces, because we're not adding up the vertices, we're adding up the spaces between the points. If you add up the spaces between the vertices for each of these three pairs of lengths, you're actually going to get 12. And that gives you a Diophantine equation of A plus B plus C equals 12. And that's interesting there. That's number of spaces. So first off is if you have a restriction here, each of these must be greater than or equal to 1. Because you have a space of 0, then you're going to degenerate triangle, you're going to line. So we can't have that. So you remember what we do? We disregard those O's that are at least one condition. So we can make this A prime plus B prime plus C prime equals 9. And that will give you 11, choose 2 equals 55 solutions to this equation. But you have to consider this. If you have a triangle that corresponds to spaces between vertices of 3, 6, 6, that's the same thing as 6. Oh, this doesn't work, by the way, sorry. I meant, sorry about that. I meant 3, 3, 6, because that doesn't add up to 12, I just wrote. So 3, 3, 6, you're gonna have 6, 3, 3 is the same triangle. And we're considering ordered pairs when we talk about balls and urns. So, but we don't want that. We want unordered pairs. So you may think, there's 3 factorial ways to organize stuff inside parentheses. Why don't we just divide by 6? That doesn't work. And obviously off the bat, because 55 is divisible by 6, but you have cases like these that have duplicates because 336 has 3 possible arrangements, and there's solution 444 which has 1 possible arrangement. So let's actually go ahead and list out the duplicates, and then we can subtract those out and then divide by 6 and get our total solutions. So duplicates are going to be 1, 1, 10, 2, 2, 8. You can just list these out, by the way. And for larger n, you can generalize these. 3, 3, 6, 4, 4, 4, and 5, 5, 2. You can't go into 6, 6 here. That's 0. Solutions, you can't have those. And these are all the duplicates. We have 3, 3, 3, 1, and 3 ways to actually orient these. And so that's the 13 possible orientations that we can subtract out of 55. And these are 5 possible triangles. So we get 42 here, and that's divisible by 6. So then we have the distinct solutions, like where the values of A, B, and C are distinct. So we can actually divide by 6 factorial equals 6 now. So we get 7 here. And these are 7 triangles here, 5 triangles here. We can go ahead and add them to get your answer of 12. And it's a very nice problem. I like it. So this will be the last problem in this lecture, and that brings us to the end of the lecture. And I hope you guys enjoyed the lecture. Please join us at our Discord link, the link provided. If you have any questions on this presentation or any problem, feel free to ask us in the Math Help channel, and we also appreciate suggestions on Discord. I'll probably have a Monday POTD on this topic, one POTD, not a hard POTD to grasp, and I'll see you guys next two parts. Thank you for watching.